Log on, tune in, find out. Another good idea from Cambridge.
About decay estimates for quantum kinetic equations. Thanks.
Thank you very much. Thank you, particularly for the invitation. Today I would like to present two recent results, in some sense connected to each other. The first one is existence of equilibrium and stability for the Wigner-Fokker-Planck equation, which is a joint work with Anton Arnold, Irene Gamba, Stefan Mischler, Clément Mouhot, and Christoph Sparber. And the second one is a factorization method for nonlinear, linear but non-symmetric operators, and it's a joint work with Stefan Mischler and Clément Mouhot. Both are very recent results, and the preprints can be found in archive. So let's start with the first result, and we consider the function u, which is a density, real valued. This is the real valued Wigner transform, and it's a function of so it's a function of space, the variable x, the velocity v, and the time t, and x and v, they belong to the R2 d. Okay? And the function u satisfies the well-known Wigner-Fokker-Planck equation, which is the first part is the classical transport term. V is scalar product with the gradient with respect to the space variable u. Then we have the pseudo-differential operator, which is a non-local operator that takes into account the effect of the potentials. Capital V is the potentials. And this, on the right-hand side, we have the collision operator. I put the subindex h bar, which is the denotes the rescaled Planck constant. So this equation describes the Hamiltonian evolution of a quantum system, which interacts with some environment, and the collision operator in this case is of a Fokker-Planck type. So we will have q of h applied to the function u is, well, we have a diffusion with respect to the space variable, then we have a diffusion with respect to the velocity variable, and then a mixed term is the divergence with respect to v of the product of v and u. This is the classical Fokker-Planck operator. I have rescaled all the constants in the front so that we have no constant. Okay, and the collision, the pseudo-differential operator theta of v. This is well known in this audience, but let me remind it what it is. Well, first of all, we consider the function u and the inverse of the Fourier transform in u. Okay, so in the theta prime variable, then becomes a theta prime, and then we have another term which is denoted by delta v, and then we have the Fourier transform of this product. So this will be d theta prime d theta. And so we have here the double integral in R2d. This is the pseudo-differential operator. And the delta v has this form, is the difference of the velocity computed at two different points. Okay, so this is classical definitions. What we would like to prove today and is the following theorem. So the main result is the following. Okay. So let me denote this equation with star. Okay, so this will be the equation star. So we will have, at the end of this talk, we will have this theorem proven. So we will prove that there exists a unique equilibrium solution for the equation star. Yeah. This equilibrium solution is denoted by u infinity, and therefore satisfies the this equation of u infinity equals the collision operator. So satisfies this equation uniquely. And moreover, if we take any solution u, x, v, and t, which is a solution of the equation star, then we have this decay. Then we have then u, any solution. Let me say one more thing. We have a solution of star, and initial data, we have u capital I. So with this function, I denote the initial data, and the mass of the initial data, I use this symbol. Okay?
Sorry, but I came late, so I probably missed what you already said. What do you assume on the potential?
Okay, 1 second. Okay, yeah, let me say the theorem, and then I will say, so for now on, I didn't say anything on the potential. I just, I say let's consider star with initial data. They have a certain mass. This is the symbol, then we denote the mass. And then we will prove that any solution of theta with this initial data will converge towards this stationary solution times the constant, which denotes the mass of the initial data, in a space. And let me use x for now on, okay? And that will be less or equal a constant, then depends on gamma, and exponential to the power negative gamma t times the ui minus the norm of the initial data minus, so how far they are from the equilibrium in this functional space x. So this will be the last, our goal. Now, let me not talk about this functional space x and what I have assumed for b. Let's keep it open. Okay, I will define v and x at the very end. Okay? Of course, one can say this theorem is not that the world was waiting for this theorem. Okay? But what is more interesting is, if this is a journey, how to prove it. In this trip was, of course, the end is interesting, but somehow the journey is even more interesting. And this is what I would like to present today. So keep this in mind, and let's consider the equation star. But now let's do a semi-classical limit. Let's consider the semi-classical limit when h bar goes to 0 in the Wigner-Fokker-Planck equation, and star converges, at least formally, to this classical transport equation. So we have now the gradient, so we have the transport term. The first one stays the same. The second one, the pseudo-differential operator with the limit, with the semi-classical limit, now converges towards a local term. And then on the other hand, we have the collision operator Q, which on the semi-classical limit reduces to the following. We have gradient in V mu plus V mu. So as you see, in the semi-classical limit, the diffusion in X disappears, and now the collision term becomes just depending on it's an operator of the second order, only depending on the velocity variable. This might remind you to the formalism of hypoelliptic operators. So on this, yeah.
I don't see where the h dependence is.
On the Q, yeah, because I was actually I wanted to write it as simple as possible. But the h depends on you on those constants in the front. And let me call it sigma of h. Okay, so in front of the three terms there are some constants depend on h. When you perform the semi-classical limit, one of them, the combination of some disappear, and this is what you get.
And what about the two?
And
It's this
So
one.
alpha goes to 0.
yeah, alpha goes to 0, yes, but you don't assume a mixed term. There should be an xv mixed derivative.
Oh, that can be, I think that can be absorbing the transport term.
No, because it's a second derivative.
No, I don't know. I don't think so.
Well,
No, I thought this is this one, no? No, I think we had that one. This is what we started with. So, we get the...
Sorry, just
Yeah.
because I'm not an expert, so but you don't have an explicit H dependency in the pseudo differential operator.
Yeah, it's over here.
the non-neutrality map.
Ah, it's there. Okay.
I think it's something somewhere over there. Okay. So in the semi-classical limit, we get the inhomogeneous Fokker-Planck equation, and on the right-hand side, the collision operator is of second order, only in the velocity variable. So this equation has been studied lately quite extensively, and many results have been proven by means of the theory of hypoelliptic operators and the hypocoercivity theory. So, more in particular, we define this function as the v square over 2 plus the, so the sum of the two potentials in the v, in the velocity variable and in the space variable. This equation has a unique steady state, which will be e to the negative v of x and v. This is quite standard. Now, the results on this equation. So when we have some literature, okay, and you will see that our problem, even if it looks very different, it actually shares many similarities with this equation. So literature for existence of solutions. We have the following. The first result is in the space of L2 with a weight given by the equilibrium solution. So L2 with this weight is the set of all functions which are in L2, such that the integral of s squared over u infinity, this is less than, this is a finite integral. And in this space, the first proof was given by Helfer and Nier in 04. And the second one was, can be found in the book of Cédric Villani. And now the space is slightly different. Instead of taking the L2 weighted with the steady state, we have L2 given with the weight of polynomial, so polynomially decaying functions. So those are the set of the functions which are in L2, such that f squared times 1 plus e, this integral is infinity, and proof of existence. Okay, so from now on I'm talking only about existence. It can be read in the EMS book of Cédric in 09, hypocoercivity. Now, what about relaxation to equilibrium? And here is the most important point. So we talk about existence, and now relaxation to equilibrium. So is it true in which space and how fast is solution of that equation converging towards, again, the equilibrium solution with the same mass as the initial data? So the first proof was given. This is why I mentioned the theory of hypoelliptic operators. The first proof was given by Hérault and Nier in 04, proving that this convergence happened exponentially fast in time in this space. So this is Hérault and Nier in 04 proved exponential relaxation towards equilibrium in L2 with the weight given by the steady state. The second one is in H1. So there is a another functional space in H1, still with the weight given by the steady state. And this is also, the proof is also in the hypocoercivity book by Villani. Okay? And the third one, which is actually I should say, those are the most comprehensive, is still in the L2 with U infinity, with the weight given by U infinity, and it's in a series of 2 papers by Dolbeau, Muho, and Schweizer. And the 2 papers are one in 09 and one in this year. Now, what is the difference between those 3? At the first glance, one can say, well, the results are almost the same. Well, the difference is that they assume different growth rate for the potential. Okay? So the first paper by Hero and Yer, they have a quite restrictive growth rate for V, for the potential V, and those assumptions are relaxed throughout the years. Now, the difference between this proof and this proof is, so the result is basically the same, but the proofs are quite different. The proof, the techniques used by Cedric Villani are actually pretty much focused on the particular structure of the Fokker-Planck. Okay, so those techniques cannot be extended to other operators. While in the series of 2 papers, actually they give a very, very general theory and method, and that theory can be, and the methods can be applied not only to divergence type of operators, like in this case, but to other type of operator, BGK, linear Boltzmann, and so on. So this is the most general proof of such a decay. And why did I mention that? Well, what they prove is the following. They say that consider, okay, let me call this equation now double star, since we have a star already in there. So what they prove is the following, that let U of x, b, and t be a solution of the equation double star, then the function u, okay, x, b, and t, minus the steady state equipped with the norm of the initial data in the L2 with exponential decay function, so equipped with the weight u infinity to the -1, is less or equal a constant c, which is explicitly computable, and this constant is greater than 1. So this operator is of hypocoercivity type. It's not a coercive operator, it's hypocoercive. So c times e to the negative at times the distance between the initial data and the steady state in all those Now, what is this one is a constant which is greater or equal 1, and can be computed explicitly, depends on the potential V. The rate alpha depends on, of course, on the potential, and is the rate then validates the Poincaré inequality, the weighted Poincaré inequality. So let me write here. So if we have, so the constant A validates the weighted Poincaré inequality, which is the following: then A times, where did I put it? Yeah, so here, u squared over u in dx is less or equal the integral of u infinity times no, let me write it this way, gradient of u over u infinity square in dxdv. This holds for any u such that the integral of u is 0. Now, why did I write the Poincare inequality for functions with 0 mass? Because this equation conserves mass, and if we the kernel of this equation is non-trivial, so actually any solution of the equation double star, so any solution x, v, and t can be decomposed in u hat plus the steady state equipped with the same norm of the initial data. Since we have conservation of mass, this u tilde will have mass 0, and this is why now the Poincare inequality will be true for u tilde. Okay, so basically every solution I partition L2 with the exponential decay into orthogonal actually spaces. One is the span of the 0 eigenfunction of the steady state, and the other one is the orthogonal, which is exactly all the functions with 0 mass. Okay? So one can work directly with functions with 0 mass and then add the, of course, the 0 eigenspace. Why? So for which potential ensures that such a Poincare inequality holds? Okay, so if one is given the equation double star, how can one be sure that such a Poincare inequality holds? Well, for example, a sufficient condition is that the Hessian of the potential has to be, in terms of, this inequality has to be read as a positive definite matrices, has to be equal than A times the identity matrix. If this inequality is true, then this condition implies the Poincare inequality. And this result has been proven by Anton Arnold, or Peter Markovich, and this was Toscani and Unterreiter in 04. So this is very important. Then we will use this, sorry?
Is it 04?
I think it's 04, no?
A bit earlier.
No, it's earlier, it's probably
But wait a second.
94.
90 something.
But never mind, but I think, yeah, it was earlier.
01. Not so much earlier, sorry. 01. 01. Okay, that was when it came out. Okay. So let's keep in mind this condition, which is sufficient, not necessary. This condition, and then the Poincare inequality. And why was did I want to outline those results for the classical inhomogeneous Fokker-Planck? Because actually the Wigner Fokker-Planck has many similarities to this, and we can apply some of those results for that for the quantum kinetic equation. So,
Sorry, just because I might get lost. So this strategy, which actually goes back to that.
oh yeah, this is very well-known result.
So in your framework, this was the one. In which of the three papers has been used? Actually? All of the three that you mentioned.
Which one?
Me. So here you're talking about the semi-classical, right? The one with h equals 0 hits, right?
Yeah.
So this is the technique that you're using, or is
No. Here I just did a review of what exists in the literature.
So this is referred to which one of the three papers that you mentioned? The last one?
No, this one is a very general result.
Okay.
So then this condition implies Poincare.
Yes.
So because here you see the v is here. This is e to negative v. So this is independent on the equation. Okay. Of course, they use this inequality in order to prove with all three.
Ah, okay.
Okay.
That was the question.
Okay, all the three. In order to prove that the decay on the in this framework. Okay? Before these techniques, or those many papers that just came out because the theory of hypocoercivity allowed to prove such an exponential decay in both space and velocity. Because this is the inhomogeneous Fokker-Planck. It's not homogeneous. What I have said, if in the space homogeneous is actually very trivial. Okay. Now, if I can,
Space homogeneous is basically
if you
0, AMT.
right, in this case we have
That one.
the
The same paper, in fact, they proved it also.
okay. Now with the inhomogeneity, then this is completely different techniques, and actually the 5 papers that I mentioned, actually 4 plus the book are the basic ones. So now what about our the Wigner-Fokker-Planck equation? Of course, one can observe right away that it does not belong to the it's not an hypoelliptic type of equation, which is in fact not, because we have both diffusions in X and in V, and this helps a lot to have the full diffusion. Though we will see then, we will borrow some techniques from here in the following way. So it is, let me clean also this one, so I don't have to stop later. So it is well known that when we consider, now I go back to the potential, okay, when we consider for the equation star potential of harmonic type, then the collision operator, the pseudo-differential operator gets simplified. And I'm not in the semi-classical limit, but still, with this potential, the collision operator still becomes a local and assume these forms. Okay, so this is actually very convenient because now I plug it into the Fokker-Planck. In the Wigner-Fokker-Planck equation, sorry. I have set again all constant to 1. And now, then we have this equation that can be rewritten in this very nice form. So I can define this operator, L of u, in this form. We have divergence. Now divergence is both in space and in velocity of gradient of u both in space and in velocity. When I don't write anything as a sub-index, this means now I'm considering a vector d-dimensional for the space and d-dimensional, so a 2-dimensional vector. Okay. So divergence of gradient u plus u times gradient of a plus another vector f, where what is a? A is now a skew quadratic form, will be x squared, I never remember this one exactly, x squared plus, it's not an exact quadratic form, this is, let me see, where was that? X squared plus 2x scalar product with v plus 3v squared, so it's a quadratic form but not exactly, and f is a vector with 0 divergence, so will be negative x, negative x, negative 3v, and x plus v. Okay, so note then the divergence of f is 0, as well the divergence of f times e to the negative a is 0. So those two properties will be used in the computations. Well, now then we have this, then if you look at this equation, so it is true that two things. So the first one is that the equation LU equals 0, so the operator L has a trivial non-zero kernel, which is given by the function e to the negative a. So even if we have a perturbation of the classical form of the Fokker-Planck, if you want to say, but f is so that the divergence is 0 and this divergence is also 0, so the steady state has the form exponential to the negative a. This is the unique steady state, and moreover it holds then the Hessian of this quadratic form a is actually less or equal than a constant sigma. Okay, let me mark it in a constant sigma times the identity. So, and this, you see what this implies. This implies that you have a Poincare inequality, which will imply exponential convergence towards equilibrium. So for this equation, ut equal Lu, it was proven in, let me see, 04 by Sparba, Carrillo, Dolbeau, and Petar Markovic, that the any solution converges towards that steady state exponentially fast in time. Okay? And where this, in which space? Well, the Poincare inequality implies exponential convergence in the space L2 with dead weight. Okay? This is immediate. So that decay was done in L2 with the exponential decay, so with the weight given by the inverse of the steady state. So with a weight of the power e to the a. Okay? So this is three standard procedure. Okay? Once you have this, you have Poincare, and Poincare implies a decay in L2 with the weight given by the steady state. And the constant in front is 1. Okay? Now, this is very nice. So the first thing then we wanted to, we thought could be very easy. It said, okay, since with that, with the harmonic potential, the Wigner-Fokker-Planck gets this nice equation with this nice form, what happens if for our potential now, we consider a perturbation of the harmonic potential. Okay? Perturbation in some sense, then I will say later. So I will consider harmonic potential and some other function V naught. So actually the equation star now becomes ut equal L of u, where L is that one, it's the divergence term up there, minus, and let me write a constant here, lambda, the pseudo-differential operator applied to the function u. So now I have a nice divergence term and some nonlinear term which I don't know, but I hope that this will be a bounded perturbation of that one. So somehow the theory should give nice results. Why? I was interested in the existence of, we were interested in the existence of the steady state. So which means that now what we need to prove is to show that the equation Lu equal lambda theta applied to the perturbation has a solution. We knew, so this is a linear operator, so what I can actually do, I can take the inverse, suppose then the inverse exists, okay, I can get the inverse applied to all the terms on the other side. This result over here, okay, implies, moreover, one more implication implies that the resolvent of L So it's not in L2, but it's a bounded operator acting on L2 with exponential decay. So this will be it's a bounded operator in the space L2 with exponential decay is actually bounded by 1 over sigma. So this is another new property that we can use. So then, since we have that, we hoped that now, how do we prove existence of this equation? Well, usually when we say, okay, we linearize, and I do an iterative process. Suppose then we knew un, I find u, and then I iterate, so that maybe I will have a contraction, and then the existence of the unique fixed point. So what we can do is we consider un minus, let's say, another solution, Vn, and here we consider u minus w. Okay. And now, since this is bounded, and we hoped that this was bounded, then we will have that u minus w in the space L2 of E minus, minus A, okay, or plus A, that's equal lambda, 1 over sigma. This is from the L1, okay. And then the theta of V naught is a bounded operator in L2 with the weight e to the A times the un minus wn. Okay. And if lambda is small enough, this should be less than 1. This is a contraction which follows that there exists a unique solution. The problem is that this is not true. This is not true, and not for some perturbations that is unbounded, otherwise can be bounded. This theta operator in the acting on L2 functions with exponential decay is not bounded. Okay? And this is a very simple exercise to prove that if you take V naught equals sinus of x time another constant k naught, this bound is not, this norm is not bounded. Okay, so then we had a problem, because the machinery was actually very elegant. We had all the estimates done, already done, and all this, it was like a puzzle. Everything fitted up to this norm. So the question was now, and the hope was to redo. Is it possible to have this estimate, for example, this decay estimate, and the decay on the resolvent, not in functions which with exponential decay, because that doesn't help for our real problem, but maybe for other functions. For example, not exponential decay, but polynomial decay. Okay? But where this term is bounded. Okay. So, and this gave actually the idea, it was the starting point, why we worked and we thought about the factorization method that I'm going to present right now. So I'm going to change the media, and I would like to switch to the projector. So, so this is the setting of the problem. Now, forget for a moment about this specific application. The factorization method that I'm going to present now is actually a very general one, and involves only linear non-symmetric operators, of every kind that you want. And the problem is the following. Suppose that we know that this our favorite operator L has a localized spectrum in a functional space, which I call it capital E. What I mean by localized spectrum, for localized spectrum, the spectrum of E is in the in a half plane of the in the half space of the complex plane. So it should be if this is the complex plane. For example, the spectrum is localized on the left of this value alpha. This is the 0, but alpha, of course, can be also negative, positive, whatever. And then on the other half plane, we have a finite number of eigenvalues. And the eigenspace associated to those eta i's are finite. Okay, so the dimension of those eigenspace is finite. So if you think about those eta be just the 0 eigenvalue, and then the finite the kernel will have finite dimensions. So this is the meaning. And we know that the associated semigroup of the operator L decays in time with this rate, with the rate given by alpha. And this term on the right-hand side, on the left-hand side, is just the semigroup which operates on the eigenspaces associated to this to the remaining eta 1, eta k eigenvectors. So if we have only the 0 eigenvalue, then this will just mean, as we said before, the mass of the initial data times the steady state. Okay, this is how those projector operators work. Now, the question is the following. Is it possible to prove property 1 and estimate 2 in a bigger eigenspace? Suppose that you know 1 and 2 only for capital E. Is it possible to show that actually the spectrum is localized and the semigroup decays in time in a bigger space calligraph E? Okay? But what you have now is just you know about the semigroup and the spectrum only in the smaller space. So, and this is, together with Stefan Michler and Clément Mouhot, we could actually give a positive answer to this problem. And the main result is somehow summarized in the following theorem. So suppose that we have, as before, we know that the spectrum of L in the small space is localized. We know that the corresponding semigroup decays. Alpha can be negative. I write it just alpha, but suppose it is a negative constant. So it decays. And we know, moreover, that the I forgot to say the following, that for simplicity in the notation, the operator is L, which I denote it by capital L when the operator is defined in the small functional space E, capital E, and I denote it by calligraph L when it's defined in the bigger space. But this is just annotation, just to have as an impact, you know, if we are talking about the operator in the big space or in the small space. Of course, the calligraph L restricted to the small space is the same as the small capital N. So, the first two assumptions are related to the problem of the operator in the small space, the one that we usually have for free. Now, in the operator or the semigroup in the bigger space, what needs to satisfy is just a mild bound. So I take the semigroup, and if one can prove that it is bounded by a constant exponential to the bt. Now b is a number that can be also positive. I don't want a uniform bound. Okay, b can be positive, but we need to satisfy this bound. And the fourth assumption is the most important one. This is called factorization, because the operator in the big space has to be factorized into two parts. The first one is actually a nice bounded operator, A, and the leftover, so B, which will be L minus A, has to be even nicer. What I mean even nicer? Then the spectrum of B in the big space Okay, now we're talking about the operator in the big space. So the spectrum of B has to be localized. So there shouldn't be any point spectrum after in this half plane. So the spectrum of B is only in this half plane. And we know that I can bound the resolvent of B in a uniformly in a line. Suppose here, this is A. Okay? And I can bound the resolvent of B along this line uniformly in Y. Okay? This is the second bullet point. Then, and moreover, the product A times the inverse of B is a bounded operator. Then it follows, for free, that the operator in the bigger space actually decays exponentially fast with the rate A. A, remember, is the point where I can, it's any real number before strictly greater than alpha, where one can bound the resolvent of B, okay, uniformly in the Y variable. So then the decay of the operator in the bigger space is given exactly by that constant. So I can get a decay rate up to alpha, but not the original one. And moreover, what is even more important is that the spectrum of the operator in the bigger space is actually the same, and well, also the point spectrum is the same, and the corresponding eigenspaces are the same. Okay. So this was a quite nice result, because one is not more restricted to use the small space where all the structure is well known by some other tools like Poincare inequality or the bounding of the growth of the potential, as we saw. This comes directly by this factorization method. So I don't think I have time to show the proof, but the proof is actually is a little bit complicated, because I want to remark that this theorem holds for both Hilbert and Banach spaces. So for Banach spaces, some estimates, like for example, the proof of dissipativity, or this is slightly more complicated, and there is some loss of norms in Banach spaces. Moreover, here for simplicity, I wrote that the spectrum of L is just the half plane and the zero eigenvalue, but actually here you can assume that you have any final number that you want of point of eigenvalues. Okay? So the proof is slightly long, and basically what is the key idea? The key idea goes from, if one has the bound of the operator in a line uniformly, then one can somehow conclude the decay of that operator uniformly in time. So the key estimate is from the point 4. So the first thing, or the most difficult thing to prove, is point 4. One has point 4, then it's easy to, from there, to have the bound of the spectrum, the localization of the spectrum, and the bound on the semigroup. But then, so once then we have this, if I would like to conclude the talk, then back to the Wiener-Fokker-Planck. How did we use this result? Well, remember we had the L operator. Now it doesn't have, we don't have this, or I don't know if you see that, but this perturbation. Now I'm just talking about the L operator. We factorize the L operator with the between A and B defined this way. And then we prove that this A and B, they satisfy all the four assumptions then I listed in the theorem. And then for free, we have that the L2 norm of the difference of the semigroup and the projection on the zero eigenspace, or so the distance between any solution and the steady state, is bounded by a constant. So here we talk about hypocoercivity. Estimates a constant times an exponential decay, and this gamma m is a constant which is strictly greater than the sigma. Do you remember sigma was this the constant then bounds the Hessian of the matrix of A. And now the new space will be L2 with polynomial decay. So we get 1 plus A to the power m. And of course the decays depend on m. So with these results, then we could somehow conclude the proof of the theorem, because now the theta operator, this perturbation is bounded, and this perturbation is bounded, so we bound the resolvent of L by the two constant, because you know then when you have, when you have something like that, then the resolvent is bounded by sigma m over gamma m. And if lambda is chosen small enough, this is a contraction property, then gives uniqueness of solutions. And so the uniqueness of the steady state was proven. One last remark was that the first one I said about the proof in Banach spaces, which is slightly different, and there is some loss of norm, because now on the right-hand side you have not the norm of the initial data minus the steady state in calligraph E, but you have it in Y, where Y is slightly smaller than calligraph E. But the second remark is that this method is a very general one and can be applied to many different equations. Not only the Wigner-Fokker-Planck, not only the classical Fokker-Planck. For example, you just told me on your fragmentation model. But actually, the most important outcome of this method was the proof of the exponential decay for the inhomogeneous Boltzmann equation. And this was a somehow an open problem for quite some time. In 2005, de Villet and Villani proved that for the inhomogeneous equation, the entropy decays almost exponential, which means polynomially with a power as high as you want. Okay, so not exactly exponentially. And with this method, since we could be able to enlarge the functional spaces, we were able to prove then actually the decay of the entropy in the H theorem. And the first time that such a factorization appeared was in 2006, where Clément-Moureaux used something similar, but in that paper it was more focused on the Boltzmann equation. So it was not such a general method, but it was more focused on the Boltzmann equation, where he used this factorization to prove theory convergence for the homogeneous Boltzmann. So that theory and hypocoercivity method allowed us to prove the exponential convergence for the inhomogeneous Boltzmann. And this, I think, Stefan Mischler gave a talk at the end of October. So I decided to skip it. Thank you for the attention.
Thanks. Any questions?
Do you have uniformity in epsilon? I missed that.
Epsilon?
In H bar.
Oh, no. We didn't.
One would really expect it, right?
Yeah, maybe. We didn't work with, yeah. It was one thing that we wanted to look at, but at the end we decided not to. I don't know for whatever reason. But of course, this is very interesting, and one should expect like that, yeah. Just mimicking the classical Fokker-Planck, then one should expect it.
The mimic problem is nice.
Yeah.
Any other questions? Okay, if not, thank you.